right, so this lab is going to be on the oxidation of benzoin to Benzil using nitric acid. So remember our benzoin is basically, it is the dimer of benzaldehyde. And once we hit this guy with nitric acid, we can form Benzil. Okay, so nitric acid being the most oxidized species of nitrogen, having an oxidation state of 5, is actually a really good source to oxidize substances, including alcohols. And so here, let me write this benzoin, Benzil. Okay, so as you can see, we created another carbon-oxygen double bond where that CO single bond used to be. And this mechanism can be pretty complicated. They say like go the simplest route, right? So that's what we're gonna go with. I will tell you, however, that the nitric acid does break down thermally because it's not very stable. And so you could have a scenario where we have HNO3, 4 of these guys, forming 2N2O4, 2 waters, and then oxygen. Okay, so this right here, it just kind of shows you that with a little heat, you can kind of break that thing down. I'm going to put that in like red, okay? And to take that a little bit further, I just want to show you real quick this guy right here, N2O4, dinitrogen tetroxide. So dinitrogen tetroxide, as you can see, at different temperatures, we got minus 196 on the left, it's colorless, and then it changes color to a darker red as you increase the temperature up to 50 degrees. And so that actually just tells you the difference. So the reason why there are different colors is because we're actually forming different species. This dinitrogen tetroxide can actually split apart into NO2. And so that's kind of why when I'm referring to the gas in this particular reaction, I'm just saying like nitrogen oxide gases. Okay, so one other thing I wanted to show you, where is it? I think actually, maybe I'm mistaken. Maybe I didn't want to show you anything. Anyway, yeah. Did I? Oh, I mean, I guess so. N2O4 goes to NO2. Whatever, it is what it is. But I did want to show you that that's kind of like, okay, we got that gas going. We're also forming other gases as we react with our product, and so yeah, I mean that's why there's just a lot of a variety of compounds in there. So that way we're pretty much just saying nitrogen oxide gas. So let's get to it. Let's get to our mechanism. Let's see. I want to shorten the benzoin. Okay, so we've got that. Here's the thing also about NO3. If you add another one, HNO3, why not just form your H? Okay, this is basically our auto ionization, and O3 minus, right? Auto ionization of water, right? We're familiar with that. Two waters make hydronium ions and hydroxide ions. So let's do the same thing here. Okay, we'll take this guy right here, we'll react it with our alcohol. So this guy can come over here and just go ahead and kick that guy out of there. Get out of there. And then boom. put that hydrogen over there. We've got our NO, O minus. We've got, I could just put my phenyl there. And then we've got this guy, right? So, let me take him down here. I'll copy that. Okay, so we took this guy, and now we have that positive charge on that oxygen, so obviously we want to remove that positive charge and give us just all the good stuff. Okay, now remember we've got this hydrogen here, so a base can come along and remove that hydrogen, create that carbon oxygen double bond, and then kick that out. So what we're ending up with is our desired Benzil product. Okay, and then we've got and 1, 2, 3, 4, 5, and there you go. Okay, so remember this guy right here can this is nitrite, right? So whoa, simmer down. Nitrite, and nitrite can form nitrous acid, but basically let's go back to this wiki page real quick. So I think I remember what I wanted to show you. Nitrous acid. So if you look at this scheme right here, I can't really point it out with my pen right now, but you have N2O4 plus water goes to nitrous acid and nitric acid, right? That if we can see that the nitrous acid disproportionates to NO, which is, as we know, is another NOx gas that's caused the problematic in smog and stuff like that. And that can be converted further with oxygen to more NO2, which can then form that more N2O4, and then can be returned to the cycle to give the mixture of nitrous and nitric acids again. So it's just like lots of stuff going on in there, right? And it's gnarly. Oh, let me click on that NO for you real quick. Let's see, where's the, oh yeah, skull and crossbones, y'all. Okay, I see you. It's gnarly. Okay, we get it, right? Hopefully we get it. Nitrogen, that gnarly looking gas is not good for our health, and so be thankful that you live in Santa Barbara with less smog than LA. Sorry for those that live in LA. I lived in it forever, and definitely enjoying the fresh air right now. Okay, so just wanted to mention, because I know y'all are gonna like bring it up. So nitric oxide, right? Toxic. But it's also naturally produced in our body. So I just wanted to point that out because that's one of those cool things where it's like toxic, but at what concentration, right? So it's naturally produced in our body. It's like a signaling thing, like, yo, chill, right? It's a vasodilator, right? So I think I read not too long ago, actually, because obviously respiratory things are going on in the world. And so I think it's produced in the nose, among other places, but like it got kind of like points out the importance of nose breathing. And so, because it helps, especially when sleeping, right? And so vasodilation, better blood flow, whatever. Also, just like relaxation, right? So that's nitric acid. It's also you might see it as like a supplement, right? NO, get you pumped, and that's basic. I mean, I don't know, I've never looked at the ingredients, but I imagine that's just a source of like arginine or some other like potent NO producer. So I think beets are like a really good source of it too. So hit up them beets because that'll get your cardio on point. And yeah, I think that's all I wanted to say about that. Before we get the lab started, because you saw the mechanism, now let's go ahead and perform it. So let's get down to business. We've had a million labs just like this. Let's get down to business. All right, let's go. Oh my God, it's about to be real today. All right, so what I'm gonna do here is weigh out about 5 grams of our benzoin, and then I'm gonna place it in here, and then I'm gonna throw both of these inside of the oven just to get them extra dry before we get that reaction started. Once I do that, I will start setting up the apparatus. Okay, it's an interesting setup, so it might take a minute, but I'm just going to show you the end result, and yeah, we'll see. Let's see what we got here. So we need 5-ish grams. So I'm just gonna go ahead and scrape some off. About 2 grams. Cool. We have 5.017 grams. Okay. I'll go ahead and close this just to make sure it doesn't change, but it should be good. 5.01. I'm hitting the bench top, so it's messing it up a little bit. 5.017 grams. So I'm gonna go ahead and place that inside of this round bottom, hopefully not spilling everywhere, but then I'll put it in the oven. Okay. Not a spill in sight, but there is a little bit of solid material kind of stuck on here. It's a little staticky. I can't get that off. So yeah, it's all good though. So the reason why we want to use 5 grams, well, generally we do have extra, right? So you may or may not have noticed that we do have a good amount extra. And so generally in this multi-step synthesis, you all as students will run through this process over like a month, right? First step, second step, now we're on the second step, and then we go third and fourth. If you run out of material because your yield is so bad, by the time you get to the end, then I would let you start over, but you're not gonna finish it probably. So you have to have good technique. You need to make sure that you're following the instructions, because if you destroy your compound, then you gotta start over, right? But a way to do that is like to save a little bit of this stuff on the side just in case you mess up, right? So if you did mess up on this and you did get a yield, right? Maybe not one that's sufficient enough to move on to the next step, you can do the reaction again with the stuff that's left over, just on a smaller scale. But ideally, this 5 grams should work. I like 5 grams instead of more than that. I don't want to put all of that in there, because for me personally, we're using nitric acid. Nitric acid's kind of gnarly. We're releasing a bunch of gas and it's nasty, and so I want to minimize the amount of nitric acid that I have to use, and so I don't want to make too much LA smog in the lab, and I think that 5 grams will be converted to enough product to go to the next step. We'll see though. All right, y'all, we're about set. Looking good. Okay, so here's my solid material, about 5 grams. We're gonna put this in a water bath. It's gonna be about 70 degrees for about an hour, If we're still evolving a good amount of gas, that nitrogen oxide gas, then we want to heat it for an additional 15 minutes and then we'll stop after that no matter what. We will heat it again 70 degrees. I don't have the heat on yet because I want to make sure that I add my 25 mils of nitric acid to this first, because it will kind of, sometimes it gets a little crazy. It needs to simmer down a minute before you start heating that bad boy up. But that's why I don't have this heating up. Another thing I wanted to point out was we want to make sure that our water level is good. So like once I put this big old round bottom in there, you see how that water level rises? Be careful when you set up your water bath, because sometimes it's like super hassle, such a hassle. Just you filled it up all the way and you got it all warm and toasty, and now you got to add your reaction flask and you're like, oh, pissed. Now I got to take out hot water from this thing. So it's a lot easier to just either check using your actual reaction flask, see if the water level's good, or fill it partially, and then it's easier to put your reaction flask in there and then add water and allow that to heat than it is to take hot water out of a hot bath. Anyway, so this guy will be connected to here. Okay. This will, so here's the thing. I told you nitrogen oxide gas will be evolved. So we're making LA smog, right? So that LA smog, we don't want to come all out everywhere, right? So what's going to happen is it's going to come up and it's going to get sucked through this tube. Follow that tube, follow that tube, follow that tube, boop, 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 bubble, bubble, bubble. There it goes. It's bubbling. It would bubble through here. So watch when I pinch this. It should stop the bubbles. It's slowing down, right? It's a little residue. You can see they get crazy. Pinch, slows down. So the bubbles, it's gonna bubble the gas through this sodium hydroxide solution. I made it about a 10% sodium hydroxide solution so that it kind of like quenches the gas, and so it's not everywhere and just spewing about. And then this guy right here, this tube just leads to the vacuum. So this vacuum is being pulled to force things to go through that way and bubble through this sodium hydroxide solution. It's there as a kind of like a way to help prevent this sodium hydroxide solution from getting sucked up into our reaction. So let's say we heat it, it starts to cool, and then we had it bubbling through here this whole time, right? So that was because of the gas expansion, and then when it cools, everything condenses down. So then there's a pressure differential between the two, and it creates a vacuum in this sodium hydroxide solution. We get sucked up inside of our reaction and destroy it. We still have nitric acid, and then we throw in some sodium hydroxide. That's not cool, right? Because acid and base directly reacting, it would be a little cray-cray. So what we want to do is make sure that we have those bubbles going the whole time, okay? That's it. So I'm gonna go ahead and connect this. Or actually, sorry, I gotta add my 25 mils of nitric acid, and then I'll go ahead and connect it, and then we'll be setting that water bath on. All right, so what I'm gonna do now is add my 25 mils of nitric acid, boom, baby, to my Benzoin. So I gotta measure that out first. Doesn't have to be perfect. Go with my left hand so you can see that better. Add a little extra. Go ahead. All right, good. It didn't get crazy. So if just in case, if you got any nitric acid on your gloves, you want to change those immediately. It'll eat straight through those. I'm gonna go ahead and I forgot to get my my chem clamp. Boom. This guy going. put that back a little. All right, now we're good to go, y'all. Want to make sure that your round bottom flask isn't touching the bottom, but it is submerged. And now I can go ahead and turn the heat on. Remember, we want to heat it to around 40 or 7. Oh, what did I say? 70 degrees? Yeah. All right. I'm gonna go change my gloves. Sitting in this lab, waiting on this flask. Gotta get the temperature. You better get there fast, cause I can't start the timer until it reaches 70. Come on, man. You're killing me. Okay, so for real though, I just made that up though, by the way, no big deal. Little chemistry rap for you. You can't start the timer for the hour until it reaches 70. So we're going to go ahead and wait. And then I'll check with the thermometer periodically. And then we can get the timer started. It's almost to temperature, which is good. Because I'm bored in the lab and I'm in the lab board. Bored in the lab and I'm in the lab board. Bored as a chemist and I'm in the lab board. Bored as a chemist and I'm in the lab board. Bored in the lab, bored in the lab, bored in the lab, bored in the lab, bored. It's at like 65 right now. We're almost there, y'all. All right, Joe. So what I ended up doing was just putting a little clamp right there so this thermometer can camp right there. And I got it so the water, it's not touching the bottom of the flask so that it gets a real temperature of that water. As you can see right now, it's about 55, which is, that's not 70, is it? Okay, so anyway, I think you can start to see some gas evolve though, right? What's gonna happen is as that rises up, sorry, I got a little something in my throat. We've got this hose, it's about halfway down, a little less than halfway. So what I wanted to mention is that when we see this gas coming up, if it gets past this point, then that means that thing's not doing its job, and we need to make sure that that's bubbling and everything is just kind of doing its job the way it's supposed to be doing. But for now, we're still waiting. Oh bother. Ooh, look at the bottom. Kind of looks like a gorgy. Maybe we're getting like a little LA sunset, you know. All right, so look at all that gas. Let's see. Oh, zoomed out too far. Okay, let's check the temperature. And I think it should be good now. 67. Okay, I'm gonna call that good. I'm gonna start my hour because we got a little 15-minute buffer at the end anyway. So here we go. So look at you can see that, oh, it's dark. All right, that's that nitrogen oxide gases. Here's the thing. See that 79? So cool thing about leaving a little extra space in there is just boom. Hit that with some room temp water just to cool it down. And there you go. Still moving, checking on it periodically, right? I'm about to go outside, but first, let's check our reaction. Looking good. All right, so the thing I'm looking for is, of course, right there. The gas isn't going past that hose, so it's doing its job. Good job, y'all. And it's at temperature. It's at 76, but that's cool. We're good with that. Yeah. I gotta go outside, get some sunlight. This is the time passing song. Time is passing, but more time than this. I'm that creepy dude walking around with a mask and goggles on. Isn't it gorgeous outside, y'all? Dang. And I'm bored in the lab. No, I'm not bored anymore. I'm having fun, as you can see. But do want to tell you, so I was thinking about it, like all this stuff, I keep showing you like blah, 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 blah. I'm checking the reaction often, and I'm not really leaving it alone because, I don't know, I'm just making sure that temperature is right where I want it. You want to make sure that you're checking your reaction often. And then if you were in a lab with friends and you needed to go to the restroom or get a snack or something, first of all, if you go to the restroom, you should have the homie check it out for you. Keep an eye on your reaction while you step away from it. And if you need to go get a snack, you always want to make sure you wash your hands first, right? I think we're professionals at washing our hands now after COVID. Probably want to keep it that forever. Okay, bye. We're stoked. I think he's ready to go. So now what we want to do is, so there is still a lot of gas forming, but I let that heat for quite a bit. So I'm gonna take it off the heat, let it cool a little bit, give it a little swirl so that the gas that's in there gets sucked up into our trap. Okay, so once that gas is gone, I am going to pour the reaction into cold water. So what I'm going to do now is get about 75 mils of cold water, put that in the freezer just to get cold, and then I will pour that reaction into that water slowly when the time has come and all of that gas is gone. Okay. Okay, here we go. I think we're pretty good now. Now what we want to do, pour this guy in here. Look at that solid material. Hit that with this real quick. Okay. Let me get this real quick with it. Sorry, you can't see it, but you know what I'm doing. You know what I'm doing. Get it with a stir bar. You can see it's cloudy, right? So this is our solid material. And so once we stir this up pretty well, we're going to go ahead and filter it off using the Buchner funnel like last time. And then we will analyze the melting point and also the thin film IR method again with methylene chloride. Okay, so here we go. Let's go ahead and get that filtration process going. Okay, so I already hit this with a little bit of that, a little bit of water, get everything all stiff. So I'm gonna go ahead and stir this up really well, and then pour that bad boy right on there. Woo, solid material, we're gonna get you out. We got a lot of solid stuck in the flask. So I gotta get my other glove on, so I shall be back. go. Knocking on solid stone wall. Alright, let's see. We can get that out. Oh. I would use a spatula. But I won't be real. I don't want to stop the video again and then restart the video after I go get that spatula. So I'm just gonna struggle getting this stuff off. But I'll get a little bit more. Basically, you can see that it's a nice yellow solid though, so that's cool. It's different than what we had. Oh, maybe you can't see. Yellow solid, right? Different than what we had. Just a little comparison. We had this stuff right here. It is a little yellow. Mostly white though. It's actually more white in my lighting than it is on the camera. But that's clearly yellow. So it's different. We'll see what the melting point and IR look like. Let that dry for like 10 minutes. Okay. Occasionally maybe stirring and poking at it just to give it a little extra help to get dry. Okay. I thought I'd tell you a little lab trick. This is actually more helpful for round bottom flasks because obviously they're round at the bottom. But you can bend. See this guy right here? Can you see that? Not really, but you know it's a spatula, right? Y'all seen a spatula before. You can actually bend them a little bit. So they're like this now. And it allows you to kind of scrape inside of here a little bit better. And that's lab tricks and tips and tricks 101. What's up? Anyway, we're still drying. I'm probably just gonna leave that in there. Alright, I just wanted to show you because it's super cool. Oh my goodness. Look at all those cool looking crystals on the outside or on the inside of that flask. That was our reaction flask. That was what I poured out the reaction out of. And obviously we left some behind and it made this gorgeous design. Check it out. Dope. Alright, y'all, we want to weigh our stuff. I already teared this weigh paper here. So now what I want to do is just throw our solid material right on top. I dried this probably like 10 minutes. It's actually pretty crispy already. Solid on here still, but I think I'm gonna go ahead and leave that there just so I don't have to sit here and scrape for an hour. Here we go. Please don't spill, Jess. Please don't spill. Ooh. 5.5. What? Where you at? Where you at? 5.576 grams. So we only need 4.41 for the next reaction. 4.4. Ah, no. 4.1. Anyway, let's just throw it in there. Whatever. We'll scale up the reaction a little bit more next time. How about that? You down? I'm down. 5.575 now is what we're going to go with. 5.575. 5, 5, 5, 5. Y'all gonna watch me. I already have enough dishes today, and I already used my powder funnel, so y'all are crazy. You think I'm gonna make another dish? Y'all are seriously crazy. Just gotta go like this. Just be careful, right? Just be careful, right? I'm trying to get this angle for you. That's actually why I'm struggling so much. Trying to show you guys. All right, there we go. All right. Look at that. You just learned today. So let's go take a melting point. Just wanted to let you know, I used the stuff that was left over in here to get my sample for my IR, my thin film, as well as my melting point. Yep. Think McFly, right? Just to conserve. So that way we know our actual mass that's in here for our calculations next reaction. Oh, okay. I think I got a little thing going on here. You know what I'm saying? I'm gonna go ahead and start that. Looks like y'all can see the best of both worlds, that temperature as well as the solid material. Nice. So, as you can see, it's quite pretty. And we started at 70. Melting point is much lower than the other one. One thing I want you to keep in mind is that it was in water, so if we see a little movement, like maybe even now, this could be due to the presence of water, because I did only vacuum it for 10 or so minutes, so it's not technically super dry, and this does in fact affect the melting point. If the solid material isn't sufficiently pure, we can technically crystallize it in ethanol. Look at that go. Looks a little weird still. Kind of looks like icy water, right? Or like not water. don't drink that water. But like solid and liquid together. You still see some stuff going on in there. Still see some stuff going on in there. Don't you worry about a thing. Don't you worry about a thing, baby. Alright. Let's keep an eye on it and see if anything else changes. Maybe this is the way it wants to be. Oh, I had it in that good position. Oh, got him back. There you beans. Looks like a cool marble. All right, I'm gonna stop it. Okay, so the reason why I wanted to stop it at around like 96 or whatever I did is because the pure Benzil melts at 95-ish, right? And so, yeah. Let's take a look at the IR that I got. Boom, 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 boom. Check it out. All right, so you're gonna wanna compare that to your Benzoin and basically make sure that some stuff changed, right? Clearly the melting point was very different, so probably good, but I want you to prove it with the IR as well. And then I'll get you a PDF of that as well. I'm trying to print this out. This guy doesn't like me right now. Look at that. He's all quiet and stuff. Anyway, I'll figure it out for you guys off camera. Bye. Wait. Are we done? Yes. Yeah, y'all don't know. I'm about to go get some coffee. I don't know where to go though. Where should I go? I don't really like Starbucks that much, but it's right there on the way home. There's the Lighthouse Cafe, is that what it's called? I'm not sure I just want coffee from home, but I want it to be in my hand right now. It's a problem. Plus I gotta get a pastry. Anyway. Struggle, man. That's what it is. So we are good to go. We converted our Benzoin to Benzil. Most likely, y'all gotta write about it, prove it to me. It is a formal lab report this week, so make sure you do that. I'll get you the PDF of the IR. We did a melting point. I didn't really talk through that because y'all can figure that out. But then, yeah, there was some errors, probably some stuff that went along. I really want you to know a lot about like why we did things today. So why we added cold water to the final reaction mixture, or why we maybe why we didn't heat it initially, right? We put it on room temperature water and then heated it up slowly. Things like that. So ask yourself, wow.